This is at least my second RavenPack conference. So these are 20-minute talks, I'm told, and I always have 5 minutes of introductory comments and leave 15 minutes for questions. So sadly, I can't actually deliver my talk at all, but we'll do the best I can. So, unfortunately, I can't attend the cocktail party later tonight, but I can tell you about a classic math problem called the cocktail party problem. So actually, it's called the cocktail party problem, but I've rephrased it to be a little more appropriate to the present scenario we all find ourselves in. So imagine a conference where there are K speakers. Now, Armando has been kind enough to let us speak one at a time, but imagine this conference, except all the speakers are talking together. And so it leads to this unintelligible cacophony, everyone speaking at the same time, and you can't understand any of them because the signals are all superimposed on top of each other. But we have the same number of microphones as speakers positioned at various points around the room. Okay, so K speakers, K microphones. Assume that the K different speakers did not agree beforehand on what they were going to say. They're not eavesdropping on each other or anything like that. So one can reasonably assume that their speeches are statistically independent signals. We'll talk a bit more about independence in a minute. The problem then is to recover each speaker's talk from the signals from all the different microphones. Okay, or in a cocktail party, you have the same problem, a lot of people talking all over the place, right? Now, I want to note already a couple of sort of symmetries of the problem, right? So we could interchange who is called speaker number one and who is called speaker number two. And it doesn't really matter. The microphones will receive the same signal, right? The microphones will still hear the same superposition of all the speakers. So that's a kind of a symmetry. We can't uniquely identify speaker number one. It doesn't matter if it's so-called permutation invariant, right? It doesn't matter if we permute the speakers. Moreover, there's another invariance in the problem. So if the speakers all speak louder, but the microphones are all turned down, that also doesn't actually affect the final recording. So there's a sort of a scale invariance. So keep those things in mind. Okay, so let xi be the amplitude recorded by the ith microphone, and let si be the waveform produced by the ith speaker. So then each microphone records a superposition of all the waveforms of all the different speakers. Okay, so we can write that in vector notation. So there's a matrix A called mixing parameters that depend on various things like the distances of the microphones, the volume, and so forth. And now, before we go on, right, I want you to all think of, what other situations in finance or in AI or in big data processing does this remind you of, right? How many situations have we all been in where what you measure, right, is a perhaps noisy representation of something that's the sum of a bunch of inputs? I mean, one could think of stock returns themselves that way, where a stock's return might have a component that's pure noise, and then it might have a residual component that's the sum of a bunch of people's trading activity. Or similarly, in news analytics, the analogy that comes to mind is there might be a few independent sources of true noise, and then they get reported on by a lot of different reporters in a lot of different ways, and then NLP extracts sentiment from all those articles, and you get a kind of a composite, news sentiment, but it's actually the sum of a lot of independent signals. It's the sum of a lot of signals, and then maybe all of those are linearly related to a few underlying independent sources. So I think this is a kind of a pretty general model. It's called a latent variable model, sometimes called factor analysis. But what I'm going to talk about is a particular kind of latent variable model in which the S's, the true underlying sources, are assumed to be not just uncorrelated, but fully statistically independent. So for example, if I put in a signal and then the square of that signal as putatively a second signal, those might actually be uncorrelated. You can construct examples of variables that are uncorrelated with their own square, but they won't be statistically independent. So we're interested in truly independent sources. Which, by the way, I've done this experiment on real data where I actually took a superposition of 3 independent waveforms and used the techniques we're going to talk about, which are called independent component analysis, to actually go backwards to the 3 original waveforms that went into it. It works pretty well. OK, so in machine learning, this is called feature extraction. We have some noisy superposition of lots of things. We'd like to extract maybe a smaller number of actual features that are driving it. It's an attempt to provide cleaner and lower dimensional representations of high-dimensional noisy data. It's worth mentioning here that in the microphones and speakers example, I assumed for simplicity the same number of microphones as speakers. That's not a crucial feature of the model. In fact, I find these sorts of things perhaps even most useful when you assume fewer truly independent sources. Again, the same independent event may get reported multiple times in the news. OK, so how do we, and if we knew the mixing parameters, and if the matrix were square, we could simply invert it, right? But we don't know the mixing parameters nor the signals. And the appropriate mixing parameters depend on the signals, right? So there's a kind of a huge indeterminacy here that we have to solve somehow. Okay, so the way to do that is some sort of statistical inference. I mean, there isn't one solution to this problem. There are infinitely many. So we need some sort of statistical model that allows us to prefer certain solutions to other ones. Okay, so it turns out that you can get most of the way there by assuming that for I not equal to j, Si and Sj are statistically independent random variables. That doesn't rule out serial dependence, of course, right? So you could apply this, again, to a superposition of waveforms where, I mean, if the waveforms are something close to perfect sine waves, then there might be a lot of serial dependence, right? That's fine. In fact, we can even utilize that serial dependence. So it's great. If Si can be partially predicted from Si t-1 and t-2, then that's great, right? I can use those predictions and to then predict the superposition as well. Okay? So this is sometimes called, this class of problems is sometimes called blind source separation. It's blind because we don't get to see the original sources, but we can separate the signal into independent components. Some people may be thinking, well, couldn't you use principal component analysis to do that? And the answer is no. It only gets you part of the way there, and it's useful as maybe a pre-processing step, so that then later when you're really doing the real ICA, you can assume that the inputs are uncorrelated. But principal component analysis does not give independent components. It only gives uncorrelated components. And moreover, it has this big indeterminacy or identification problem, right? As you all know, those of you who have worked with principal components, they're not identifiable. They're only identifiable up to a rotation, right? In principal component analysis, you essentially do an SVD and you identify orthogonal bases of the input space and the output space. But those orthonormal bases you could apply a rotation matrix to get them to some other basis. And that's also a perfectly good principal component decomposition. So So any orthogonal transformation is also correlation 0, so it's kind of highly non-unique. Some people call this the factor rotation problem. It turns out statistical independence is a much stronger statement, and it basically eliminates this, this factor rotation ambiguity. Okay, so if we insist that the components are not only uncorrelated but actually independent, then we can get an almost unambiguous identification of the independent components. As I mentioned, there's always going to be an ambiguity of reordering the labels on the sources. You know, if we switch what's called source 1 and source 2, the superposition of the sources is going to be the same. So we shouldn't expect to somehow, in fact, it would be wrong if we somehow got a solution that didn't have permutation invariance. It has to have permutation invariance. Similarly, rescaling the source and then also simultaneously, scaling up a source and simultaneously scaling down the input, the matrix of input parameters is, we haven't. That ambiguity will still remain even in independent component analysis, but that can be that's usually resolved by simply assuming that each Sj is a random variable with unit variance. So essentially fixing, since the scale of the Sj is arbitrary, it's only the combination of the Sj times A that matters. You may as well fix the scale of the independent components. Okay, so this is something I've been working on with my collaborator, Petter Kulm at NYU. Petter and I have collaborated for many years. Some of our work relates to multi-period portfolio optimization and transaction costs. Some of our work relates to reinforcement learning and other things around multi-period dynamic problems, basically. So this is a little bit of a new direction for us. So we've been thinking about specifically the problem where the number of sources might be a lot less than the number of microphones listening to those sources, right? And again, you could think of a stock as a microphone whose price return, responds to all these sources, right? A stock's price is an expression of what's happening to that stock, and news sentiment about a stock is an expression of it's the aggregate news sentiment for a stock is a superposition of a lot of independent sentiments from a lot of different articles that pertain to it. But again, although there may be many articles, there may be few truly independent sources that are driving all that activity. So that was kind of our impetus for looking at this. The number of independent sources then can be viewed as a model complexity parameter, analogous to the tuning parameter in Lasso, the number of weights in a neural network. Every machine learning problem that I know of has what I call a model complexity parameter. Sometimes several. Sometimes there's a model complexity parameter space. But let's say, for simplicity, there's one parameter. It parameterizes between a more complex model and a simpler model. And more complex models are prone to overfit. Simpler models are prone to miss features. Simply put, right? So here, one model complexity parameter, a particularly important one, is how many truly independent sources we believe are driving this higher dimensional system that we live in. So we've been looking at ways of choosing the appropriate level of model complexity. For example, cross-validation is one. So that's been pretty interesting work. The goal here is really that, again, some sort of denoising and a very convenient lower dimensional representation of higher dimensional data, right? We have, anywhere from 5 to 10,000 stocks globally that are liquid enough to look at if you're an institutional investor. So that's a high dimensional system. We're looking for the best lower dimensional set of components to represent that system. And similarly, again, news sentiment on 10,000, a 10,000 dimensional vector of news sentiments might be driven by a million-dimensional space of stories, which themselves might be driven by only 10 truly independent sources. That's the sort of model we're considering here. And the hope is that one can forecast, well, okay, if you can forecast the underlying independent components, the S's, then you can also forecast the observations, the X, in the obvious way. X is linearly related to linearly related to S, so a forecast of S leads to a forecast of X. And even better if the S's are, in some sense, denoised, right? Because the original model had a noise term in it. We estimate the noise term jointly when we estimate A and S. So, so the S's are the result of a denoising procedure in very much the same way that, in the Kalman filter. The reason it's called a filter is historically was related to the fact that it was used for filtering out noise. So the S's are the result of a filtering process that's intrinsically denoising them, and hence may make it much easier to forecast the S's than the X. So assuming the S's then do have this time series dependence, that ST is predictable from ST minus 1 and so forth, then that gives a nice way of forecasting the original variables of interest as well. So roughly speaking, again, this corresponds to the view that a Stokes return is like what the microphones receive in the cocktail party. It's the end result of superposing a lot of different individual activities that could be thought of as traders in the market. But traders in the market are not independent, actually. They may all be reacting to a few truly independent sources. So we believe this technology gives a way to estimate the few truly independent sources. So I wanted to have a few minutes for questions. So perhaps I'll stop there.
Okay. So we have one question right in the middle. If we can bring the mic over, please.
Just a quick technical question. You have to assume that A is constant in this scenario. Can it be time dependent or stochastic?
That's a good question. I mean, if it were allowed to be fully independent in each period, then I think that would lead to a much larger indeterminacy than the one in PCA, right? If every single period, both the coefficients and the states are allowed to be different, then. But perhaps some kind of very slow-moving A could certainly be modeled. Absolutely.
Great. Thank you very. Oh, well, sorry, we got one more question over here. Someone got a mic to bring over? Oh, okay, we got two, but we got time for one more.
So I have actually two questions. So the first one is that, is there anything we can do? The ICA assumes that the mixture is linear, right? Mm-hmm. What if it's not linear? This is first. Second, we normally maximize a measure of non-normality, right, to do it. So can you comment on which measures of normality are the best to do it?
Sorry, you say we normally example, maximize what?
Some measure of non-normality.
Yeah.
So
I see.
Yeah. So you can measure non-normality in different ways.
Mm-hmm. Well, actually, I mean, you can think of it as maximizing non-normality and hence, kurtosis. Or you can also just write the whole thing as a big maximum likelihood estimation, right? Where you're jointly estimating a likelihood function that depends on A and also S, right? And it lends itself well to maximum likelihood estimation because under the independence assumption, the joint density of all the S's factorizes. And so you're left with choosing a density, some sort of prior density on each component of S. And so, I mean, there may be cases in finance where you do have some natural prior on the independent components. So I like those methods personally.
Great. Let's give a big round of applause for Gordon Ritter.
This is Raven Pack.